Well, it all starts with counting apples. I mean, you can't change the number of apples without changing the number of apples, can you? Addition. If I have 3 apples and you have 4 apples together, 7 apples. Multiplication. 3 apples in a column times 4 columns, 12 apples. So multiplication is just repeated addition, right? Well, yeah, and no. And what's the difference and why? That's what this video is about. That and exponents. 3 to the 4th power. Well, exponents are just repeated multiplication, right? Well, kinda. Anyway, get your apples ready. A column of 3 apples. 3 of those columns makes an apple square. A row of 3 apple squares, that's 27. 3 rows, each with 3 apple squares, and we are running out of apples, but we are happy because it all goes back to counting. Or does it? First, let's notice that order matters not. Not here or there. But it does matter with exponents. Base war. Quick question. Could you solve this problem? If not, see part 2. Addition, multiplication and exponents, and a knife. 3 1/4. Okay. A group of 3 of those quarter apples. That would be 3/4 of an apple. Okay. But what exactly does it mean to multiply the number 3 by itself 1/4 of a time? I'll tell you what it means. It's unsettling. Negative fractions. I start with 3 apples, and then I take a 1/4 apple bite. It leaves 2 3/4 apples left. Or 3 of those 1/4 apple bites would remove 3/4 of an apple. And I'm already sick of exponents. Fraction party. 1/3 plus 1/4. I remember this, the common denominator. 7/12. And you might remember an algorithm for multiplying across the so-called top and the so-called bottom. 1/12. You see, I got this awesome way of eating apples. It's a 4-part process that ends up eating 1/3 of the apple. So just one of the 4 parts of this process eats 1/12 of an apple. Got it? I think I got the order wrong on that one. Hey, exponent guy, you're not cool. Wait a minute, that is kind of cool. But no one cares. Don't be so negative. I eat 3 apples. You eat 4 apples. Together, the company is down 7 apples. Multiplication. A negative times a negative is a positive. What does that mean? When I work, I eat 3 apples from the orchard every day, but I was sick 4 days last month, so that's 12 apples I didn't eat. And the exponent guy, like we said already, is not cool. Wait a minute, that number is kind of cool, but it's missing an 8. Hey, anyway, try this with your calculator. Try this with a 4.5 instead of a 4. Wait, no, don't do it. It's too dangerous. That's part 3. And I don't know about part 3, but part 1 seems to be useless and pointless. You told me that multiplication was not repeated addition. But it is, even if apples aren't very useful. But what about string? 3 meters plus 4 meters makes 7 meters long. That's string. Or an area, 12 square meters. See, a grid of 12 1-meter squared squares. Focus on units. Apples plus apples gives you apples, but meters times meters gives you square meters. Or consider distance equals velocity times time. Travel at 3 meters per second for 4 seconds. You go 12 meters. But how could addition do that? And how could you picture that? Maybe on a graph. Here's a distance versus time graph. And the line goes away, but you come back because there's no way addition could do the cross product, if you know what that is, 3 perpendicular vectors. Or matrix multiplication. Gross. So my point is that addition, multiplication, and exponents are really different. But how? Let's get general. Starting with addition, y equals alpha plus x. And that's a look at it graphically. We could start with any alpha. Let's start with 0, y equals x, or alpha equals 4. Everywhere on this line, y is equal to x plus 4, or negative alpha. Line shift. And there's an example, x in blue, y in red, both of them positive, but alpha is negative. Here's how it looks flattened out. Again, here x and y are positive, x is bigger. Shorter vectors, x is still bigger. Negative vectors, get some time. This time y is longer, but y is always on the left of x. That's what the equation says. Yellow tiger is always to the left of x the owl. They move around a bit, but y is on the left. As long as alpha is negative, that is, for a positive alpha, y is on the right. The bigger the alpha, the farther they are apart. Alpha is the slide you around function. So much for addition. What about multiplication? Y equals beta x. Here's the graph for beta equals 1. Or beta equals 3. We've seen this before. Or beta equals negative 1/2. Downward slope, not steep. Back to beta equals 3 with arrows. Beta is a scaling factor. Small changes in x become bigger changes in y. Negative x, no problem. Back to beta as negative 1/2. Here, x is negative. It's the make them smaller, change them direction function. Here, x is positive. Y is negative. Hello again, x the owl, y the tiger. With addition, you guys stayed the same distance apart. That is no longer the case. Farther or closer, same direction or opposite, we are stretching. Addition slid, multiplication stretches and skews. They are different things. And you'll recognize multiplication as a stretcher if you recognize the dot product. It's related to this length, the component of A along the vector B, or the cross product, which is related to the area of that parallelogram. Sine and cosine. Again, part 3, more on that stuff. The point here is that multiplication is more than just repeated addition. Yeah, okay, it is repeated addition, but it's more. It's different. Ready for exponents? I'm not, because I need to say this. Alpha and beta become alphas and betas. Here is something clever. What if alpha equals x? That means y is equal to 2x. That's not funny. I don't like the fact that you did that, because you just had me thinking that they were different. Now they're the same. This is pointless. I was right. Well, they are different. One stretches, one slides. How about letting beta equal x? Y is equal to x squared, or x is equal to the square root of y, or any power. And one more thing. Addition, undone with subtraction, the inverse operation. Generally speaking, and a random value for x, y is bigger. Here's the inverse operation, x is bigger. It's the find your friend function. Hey, owl, where's your friend? To the right. Hey, tiger, where's your friend? To the left. Multiplication, undone with division. Consider this function. At a random point, y is longer than x. The inverse function, y is shorter. Hey, owl, tell me about your friend. Oh, he's crazy. I move a little bit, he moves a lot. Hey, tiger, tell me about your friend. He's lazy. I run all over the place, he barely budges. Addition slides, multiplication stretches, different relationships, and exponents are next.